Hello, my name is Diana Pawlicki and thank you for taking your time to listen about in situ production of reagents for liquid fluoride thorium reactant on Mars. While this presentation and paper stands as a continuation for the one I co-authored on last year's ISC, I am aware that many, if not most of you, didn't have the opportunity to get familiar with it, hence why I want at least the presentation to be a bit of a standalone piece. Therefore, some basic information must follow precisely as to what the LFTR is and why it is the best choice. LFTR, or lifter, is a type of molten salt reactor, which means it operates on molten fuel. On the GIF I'm very proud of making, you can see its basic cycle. There is no meltdown risk here since the fuel is already molten, and in case of any failures, the fuel salts would escape into the damp line beneath, which is usually closed by a freeze plug made out of frozen salts. Operating on high temperatures of around 700 degrees Celsius, lifter can operate with thermal efficiency, incorporating heat to electricity of circa 45%, which is higher than nowadays 33%, and can potentially be even higher, up to 50%, due to the usage of closed-loop supercritical CO2 Brayton cycle power conversion system. When it comes to my focus though, it's ISRO. Because so what if we could build a very efficient power conversion system on Mars if we would have to ship everything there? All we need for running the production line for the reactor is there, on Mars. But before I get into describing stuff that is there, we need to know what do we even need there. LFTRs use liquid fluoride salts as both coolant and carrier for thorium and thorium-derived fuels. Fluorine salts are strongly ionic and when melted are stable at high temperatures, low pressures and high radiation fluxes. However, fluorine is likely to form compounds and thus various salt possibilities were theorized. Notably, tested cases used sodium fluorine compounds, often avoiding the usage of lithium at all, but as lithium does prove to have great properties for such usage, mainly lithium fluoride having excellent heat transfer properties with volumetric heat capacity around 22% higher than water, I focused on the three main salt options containing that. Importantly, zirconium and sodium fluoride are comparable in production properties, so the last salt serves as a kind of a summary point. Based on research, the best choice would be lithium fluorotetraberylate, also called FLiBe. However, due to tritium production and relatively low abundance and high toxicity of beryllium, it is reasonable to research other possibilities. It is possible to operate instead using lithium fluoride, thorium fluoride, authentic without beryllium. This comes at the cost of a somewhat higher melting point, but has the additional advantages of simplicity, avoiding beryllium fluoride in their processing systems, reduced tritium production, and improved heat transfer. Alternative solvents such as fluorides of sodium and zirconium allow lower melting points at a trade-off in breeding. Now into the resource abundance. LFTR needs thorium and gamma-ray spectrometry of the mid-latitude region of Mars shows abundance of approximately 0.7 ppm, I think you can see on the image on the right. However, in the case of volcanic Martian rocks, thorium concentration reached 5 ppm. Compared to 1.1 ppm for uranium abundance, it can be stated that the concentrations are similar to terrestrial basalts in consideration with the planet's scale, which not only makes thorium a viable fully fuel reagent for nuclear power plants on Martian surface for settlement purposes, but also proves a thorium-based fueled reactor to be a better choice. The image on the left concerns fluorine. Scanning on Mars surface using MSL's ChemCam returns the presence of fluoride, which is the Earth common mineral form of calcium fluoride and source of natural fluorine. While there is no Earth to Mars abundance comparison available, it is safe to assume Mars to be a rich or at least comparable fluorine source. Moving on to lithium and beryllium, perhaps two of my favorite elements, as you can see there's just one table which contains estimations for bulk planetary abundances for both of them. This is because both lithium and beryllium have relatively low universal abundance and are likely to form compounds, hence why their bulk presence had and has to be estimated. Bulk planetary abundance for beryllium for Mars has been calculated to reach 88 ppb. Compared to Earth's 45 ppb, Mars should be a rich beryllium source, even though no beryllium-based material composites have as yet been confirmed on Mars, although trace amounts of beryllium have been found in Martian dust, which confirms its planetary presence. As to lithium, likely research into materials examined to have originated in Mars shows the presence of lithium. The Mars Science Laboratory MSL Curiosity rover includes for the first time the capacity of directly detecting lithium via its ChemCam instrument. Lithium contents measured by MSL in materials within Gate Crater are low and variable, mainly between 5 to 10 ppm, similar to terrestrial mid-ocean ridge basalts. However, maxima are up to 60 to 80 ppm. Smectite clays such as hectorite have been suggested as possible host minerals for the lithium identified in Mars with MSL, which is great news considering hectorite-like clays being the main source for lithium production on Earth. Zirconium presence on Mars could be safely expected, as zirconium silicates formed after lava cooldown and Mars is known to have 4 now extinct volcanoes. Notably, some researched meteorites contain zircon grains. Sodium chloride is the most common salt on Earth, and it's common on Mars, particularly in the planet's southern highlands. Perchlorates have also been detected at the Phoenix Lander and Curiosity rover landing sites on Mars. It can be safely assumed that it's widely present as fluorides and sulfates, and can be partially seen in Hemk analysis spectrum of the coronation soil/rock sample. Now, having the basic evidence of resource presence on or in Mars, we can move to the production chain. I'm not a chemical production engineer, so I didn't engineer those, of course, but as much as I can say, the process follows the route on the slide. Reduction in size, starting with base, heating, filtering, heating again, acidification, basification, removal of solids, and hot filtration. The end result is lithium carbonate, a white granular solid. Lithium fluoride can then be produced by a reaction of lithium carbonate with hydrogen fluoride. Lithium in nature is composed of lithium-6 and lithium-7, two isotopes. FLiBe needs highly enriched lithium-7. Luckily, this isotope is 92.5% of the natural lithium, which simplifies the enrichment requirement. Things get a little more complicated with beryllium tetrafluoride, even though the slide doesn't make them seem as much. It's because, as I mentioned before, there is no clear evidence of beryllium in compounds, and one cannot really make a production chain without the main reagent composition being known. What is shown here is a theorized version. Assuming the compositions would be similar to those on Earth, sulfuric acid leaching scheme, nowadays mostly used technique, is highly problematic. Proposed is the ammonium fluoride technology for processing of beryllium-containing raw materials, which follows the 4 points route shown on the slide: fusion, dissolution, purification, and evaporation. In case of this proposed method getting declined, perhaps because of the need of sulfuric acid for lithium fluoride production anyway, the resulting salts would need to be purified of leftover sulfate ions. Here the proposed solution is repeated crystallization of ammonia tetrafluoroberylate using 5:1 water ethanol solution. The result, of course, is ammonium tetrafluoroberylate, not just tetrafluoroberylate, but this precursor is actually a reagent needed for the production of the salt. FLiBe is formed by synthesis of lithium fluoride and ammonium tetrafluoroberylate, that being the only known to date way to produce the end result substance. High purity is required, therefore the aforementioned main reagents have to be additionally prepared, specifically vacuum oven dried, of excess water that might have been left from the production process. The reagents are mixed and added to a graphite crucible, which gets sealed in a vacuum induction melting furnace. The furnace chamber is then recharged with high purity nitrogen to permit a minimum positive pressure, and the mixture is melted according to a preset temperature program. Of course, this method is derived from another paper, as extensive practical study has been impossible for me for a variety of reasons, with global pandemic contributing to the cause, so huge batch production might differ in used methods and/or proportions. After completion of melting, salts are transferred to an airtight storage tank and cooled naturally to room temperature. And that's how FLiBe is made. As presented, FLiBe has an extensive research coverage of all its aspects. This is not true for lithium fluoride, thorium fluoride, acetic acid, or zirconium, or sodium salts. Both of those need lithium fluoride, production of which has just been described. When it comes to thorium fluoride, it can be produced by reacting thorium with fluorine gas. The production of the acetic itself is similar to lithium tetrafluoroberylate process with the usage of a vacuum furnace. It is important to notice, though, that in the case of fuel cells, this substance requires heavy nucleate proportion of 20 to 30 mol%, with operating temperature around 570 degrees Celsius. Lithium fluoride thorium tetrafluoride is no longer liquid at higher temperatures, as shown on the attached picture, and the salt would require an addition of beryllium in order to lower its acidic point and keep the operating temperature. Similar thing concerns zirconium and sodium, hence why the beryllium addon has been included in the formula there. Here's a quick detailing of co-reagents production. Common ingredient here is sulfuric acid. It has rather complex and troublesome ways of production, which can be remedied by electrochemical splitting of sodium sulfate into sodium hydroxide and sulfuric acid. Nitrogen needed for ammonia is found in Martian atmosphere, and thus can be derived from processed air and catalytically reacted with hydrogen. Concluding this described salt production processes, widely proposed FLiBe in fact poses as the best candidate, mainly due to its rich coverage in research. The issue of low beryllium abundance and toxicity has not yet been solved, although this paper assumes a degree of process automation and does lower chances of health effects on humans in case of a safety breach. Tritium production in turn can be used for fusion research. Personally, I think more attention may be paid to lithium fluoride thorium tetrafluoride acetic, as while rendering barely worse results in efficiency, it is not only safer to produce but also more reliable as per the current state of knowledge, given beryllium presence has only been estimated. I might even take that as my next research paper topic too, who knows. There are many areas of development and opportunities in this field, and I very much hope I did give an understandable yet resourceful look into the matter. Ending this all, I usually like inserting a quote of a wise person. But since for whatever reason I decided to reference every single little thing in this paper and ended up with 25 reference points and lack of a place on the slide, I'm just going to say it. In the middle of every difficulty lies opportunity. and we must never forget that. Thank you.